Hi friend, welcome all to my educational channel Math A to Z. We already know from the previous class of group theory that the intersection of two subgroup of a group is always a subgroup of the group. But union of two subgroup is not always a subgroup of that group. And also we know that in what condition union of two subgroup becomes a subgroup of the group. Now in this class we define another type of set operation between two subgroup of a group. We first define here H into K as a new type of subset or new type of set, and this set is defined as H into K such that H belongs to H and K belongs to K. K belongs to K. This is the definition of HK. If H and K are two subgroup of a group G, then HK may or may not be a subgroup of G. For example, if we take the group S3 and let H is E, we know that this is a subgroup of S3. Also, if we let K this as E13, this is also a subgroup of S3. But from this definition, if we calculate HK, then we get HK is equal to E13, 1, 2, 1, 3, 2. And we know that this is not a subgroup of S3 because S3 has 6 subgroups. One is improper, one is trivial, and other 4 are this, and so this is not in the list of all the subgroup of S3. So this is not a subgroup of S3. Now here we try to find under what condition HK is also a subgroup of the group G. To prove this or to find the condition, here we state the condition together with its proof as let H and K be two subgroups of G, then the following are equivalent. First is HK is a subgroup of G. Second, HK is equal to KH, and the last is KH is a subgroup of G. These three conditions are equivalent. Okay, now we first let the first condition hold. That is, we let HK is a subgroup. And from this we try to prove 2. That is, HK is equal to KH. And to to prove this, we have to show Hk is a subset of Kh, and also we have to prove Kh is a subset of Hk. Okay. At first, we let two elements K belongs to K and H belongs to H. Then obviously K into H belongs to KH. Now we try to prove this element KH is also belongs to HK. Then we can write this. Okay. Here K belongs to K and E belongs to H, because H be the subgroup and E be the identity of H. Then E into K, this is belongs to HK from the definition of HK. Also H belongs to H and E belongs to K, because E is the identity of K. Then H into E, this is also belongs to HK, and this relation gives K belongs to HK, this is small k, and this relation gives H belongs to HK. And since HK is given as a subgroup, so by the closure property we must say K into H, this is the closure property, must belongs to HK. So we start from this and we end at this. So for all KH belongs to KH, imply KH belongs to HK. That is, we can write from this and this, KH is a subset of HK. This is the first target. Now we try to prove HK is a subset of KH. And for this, we first let HK belongs to HK. And HK is a subgroup, so it must have HK inverse belongs to HK. And since HK inverse belongs to HK, so we can write HK inverse in the form of H1 K1. Okay. Now HK inverse is equal to H1 K1 belongs to HK. Now we have HK here. Now we have, if we take the inverse on both sides, we get HK, this is equal to H1 K1 whole inverse, and this must equal to, from the inverse property, K1 inverse H1 inverse, because AB inverse is equal to B inverse A inverse, and this element K1 inverse must be an element of K, and this element H1 inverse must be an element of H. So the whole element must be belongs to KH from the definition of KH. Now we start from this HK belongs to HK and end at HK belongs to KH. So we say that HK is a subset of KH, and this is our second target. So from this and this we must say HK is equal to KH. This is the proof from 1 to 2. Now we try to prove from 2 to 1. Okay, here we let Hk is equal to Kh, and we try to prove Hk is a subgroup of G. That is, this belongs to this. So here we first let H1 K1 and H2 K2, two element belongs to Hk, and from the property of subgroup we know that if A, B belongs to a subgroup H, then if we belongs to a subset H, then if we can show A, B inverse belongs to H, then we say that H be a subgroup. Okay, and we apply the same process here. We first find H2 K2 whole inverse, and this is K2 inverse, H2 inverse. Now we calculate H1 K1 composition H2 K2 whole inverse, and this is H1 K1 K2 inverse H2. Now by the associative property we can get K1 into K2 inverse as, okay, because K1 K2 both the element of K, and K be a subgroup, then we can write K1 K2 inverse belongs to K, and we take this as K3. K3 belongs to K. Now since Hk equal to Kh, then this element K3 H2, this is H2, can be taken as H4 K4, because Hk and Kh are equal, right? So we write this relation as H1 into H4 K4. Now we also apply associative property as H1 H4 into K4. Here H1 into H4, this is also an element of H, and we take this is H5 and this is K4. So this element belongs to Hk, that is belongs to Hk. Okay, so we see that if we take any two element, this and this belongs to Hk, then the first element into the second element inverse belongs to Hk. So from the property, this property, we say that Hk must be a subgroup, of G. Okay, now we prove from 2 to 1. Similarly, if we take 3 and 2, this proof is also same type, because here Hk is a subgroup, then Hk equal to Kh, and we get if and only proof. Similarly, if we get 3 and 2, then we also 3 imply 2 and 2 imply 3. So we say that this and this 3 relation are equivalent. This theorem can be stated as if Hk is a subgroup of G, if and only if Hk equal to Kh. Also we stated as KH is a subgroup of G if and only if HK is equal to KH. Right? And here we state an important note that if we take G as a commutative group, then always HK equal to KH for all subgroup of G, because if G is commutative, then all the subgroup of G are also commutative. Then we say that for commutative group, HK is always a subgroup of G. But here important to notice that commutative property not necessary for proving HK be a subgroup, because here we get an example of non-commutative group, but HK is also a subgroup of G if H and K are the subgroup. We know that if we take G equal to S4, that is the symmetric group of 4 symbol, this is must be non-commutative group. And if we take 2 subgroup, the first as H is as E 1, 2, 3 and 1, 3, 2. And if we take K as E and 2, 3. Here obviously if we calculate HK and if we calculate KH, then both are same. So HK must be a subgroup of G. But here S4, that is G, is not commutative. Okay, so to become a subgroup HK, it is not necessary that G must be a commutative. So commutative property is not necessary for this, and this is the important example to show the not necessary condition. Right? Now we go to another important observation, that if H and K are 2 subgroup of G, then HK may be a subgroup of G or may not be a subgroup of G, right? But H and K, since both are the subgroup of G, then both are non-empty. This is not equal to phi and this is also not equal to phi. So we say that HK is not equal to phi. Either this is a subgroup or not. Now we try to find the number of element of HK. That is, we denote by order of HK, or it is also denoted by order of HK. So we also state a theorem as, let H and K be 2 subgroup of G, then the subset, not subgroup, the subset HK as order of HK, or order of HK is equal to order of H into order of K by order of H intersection K. Okay, this is also an important theorem. Now we go to proof of this theorem. Proof. Here H and K are both the subgroup of G. Let order of H is equal to M and order of K is equal to N. And also we take order of H intersection K, that is the common element of H and K. This is also a subgroup of G. This is P. And since we take this is M, this is N and this is P, so we can write H is equal to H1, H2 to Hm. K equal to K1, K2 to Kn. And H intersection K is taken as T1, T2, Tp. Okay. Now here we define or we write Hk as Hi into Kj, such that Hi belongs to H and Kj belongs to K, where I lies in the range this and J lies in the range M. It is clear that if Hi and Kj be an element of Hk and if all the elements are distinct, then the number of element of Hk is equal to order of H into order of K. But this list may not be distinct. Okay. Now we have to find how many times an element, any element, say H1, K1, may appears in this list. Okay. Now we first take, let H1, K1 is equal to HR into Ks. This is in this list, also this element in this list. And from this relation, we write H1 inverse into HR, and this side is K1 into Ks inverse. Okay, we operate Ks inverse from the right and we operate H1 inverse from the left. Then we get this result. Since H and K both the subgroup of G and these are the element of H, also these and these are the element of K, so we say that this left side is an element of H and the right side is an element of K. And element of H and element of K are equal, so it must be also in H and also in K. That is, we say that this element must be in H intersection K. Let it be TL, where L is from the range 1 to P. Now from this relation, we get HR is equal to H1 into TL. From this relation, we can write S is equal to TL inverse into K1. Okay, this is H1 into TL and this is TL inverse into K1. That is, we say that any element HR into Ks can be written as HR into Ks can be written as H1 into TL, H1 into TL into TL inverse into K1. Okay, where TL belongs to H intersection K. So HR into KS, this element can be written as this type, where TL belongs to this. Now if we take TL as T1, then there is an expression of HR into KS. Similarly, if we take T2 in place of TL, then we get another expression, and for all the TI or all the TL, we get another expression of HR into KS. That is, we can say that here we get T1, T2, TP for each T, and another expression of HR into KS. That is, we say that HR into KS appears in this list. In this list, what times? P times, because here P option T1, T2 to TP. So one element appears in this list P times. So the number of distinct elements in this list is given by M into N by P. Because here if all the elements are distinct, then here the number of element is order of H into order of K, and this is M into N. Since one element appears P times, so the number of distinct element here is given by this result. So we say that order of Hk is equal to Mn by P, and this is order of H into order of K by order of H intersection K. Okay, this is complete the proof of the above theorem. Now here important to notice that if for two subgroups here, if only one element E identity belongs to H intersection K, then this is 1, right? So in this case, order of Hk is equal to order of H into order of K. Okay, and if Hk becomes a subgroup, then we can also find the order of the subgroup Hk of the group G from this relation or from this theorem. Okay, and these two are the today's topic of class. Thank you.